Hi all, I want to welcome you to the first recording of this module 3. Today we'll be looking at the periodic table. That is what we'll be talking about today, the periodic table. Of course, one of the commonest things we talk about every day is the periodic table. I usually tell my students that the periodic table is the Bible of life. It's the Bible of this world. And today we're going to have a friendly look at what the periodic table says. So let's start. Usually in every beginning of every module, I usually open it up with a quote. This quote is from Drew Brees, a very popular, I would assume a Hall of Famer football quarterback with the New Orleans Saints. He says, "Nothing is given, everything is earned. Just know that whatever you want to get in this life, whatever you want to do, whatever you want to be, nobody gives it to you. You go earn it. How do you earn it? Through hard work, through perseverance, through consistency. And I want to promise you that as you even persevere and work hard in this class, whatever you desire and deserve to get, you're going to get it as we move on. All right, let's open up the class. The first thing we need to look at is the learning objectives. As usual, I'm not going to be reading the learning objectives, but I want you to take time to read these learning objectives and put them in your flashcard, your learning goal flashcards, so that you can easily go back to them and check mark them if you have actually understood them by the end of this lecture. The periodic law. From the name, as the name implies, the periodic law states that the properties of elements are a periodic function of their atomic number. Now, the word periodic, it's a common word used in everyday society, which simply means that something can occur at intervals in a repeated pattern. And that is exactly what we see in the periodic table. You see, if you take a look at this, my small periodic table down here, let me try to use a pointer and see that. If you take a look at this, my periodic table down here, you find out that you can notice a different pattern. First of all, what we can see here is that there's a serial number that we have at the top of this place, and that in the first place we'll talk about them is the families of this element in the vertical columns. And as we go down, we see another pattern that reads from 1 to 7, which we call the groups. We're going to see that as we move on. So as we go either down this group or across this periodic table, either we go down the group or across this periodic, we're going to notice some characteristic pattern which we're going to study as we move on in this class. So chemical and physical properties of elements will reoccur or show a periodic variation in the periodic table when arranged in order of atomic number. That's exactly what the periodic property is talking about. So a good example is that if you look at elements in this group minus hydrogen, that of course is a non-metal. All metals in group 1, from lithium to francium, will have a similar chemical properties. They are not going to have the same chemical and physical property, but they will have a similar chemical property that can be predicted in a specific pattern. The same goes for each of these groups, as we will see. So let's see what we got in the next slide. So the periodic table itself is arranged based on the knowledge of this periodic law into two ways: into the vertical columns and into the horizontal periods. Now, the vertical columns, so as I said, now the vertical columns represent the groups, or what we call the families of this element, represent the groups, or more better, we describe them as the families of elements. And it makes sense that each of them in this family, of course, will have a specific pattern of behavior, very similar, that can be predicted, as we see. Now, like I said earlier, this arrangement is the very most important arrangement we're going to see in the periodic table, because we said arranged into vertical columns and horizontal rows. The horizontal rows are the periods. We call them the periods. Now, in modern periodic table, elements with similar chemical properties are found in these vertical columns. Of course, we call them their groups or their families. So if you look at the periodic table I have here, the periodic table is actually made up of about 7 rows. Let me try to fill them here. So this is row 1, this is row 2, this is row 3, 4, 5, 6, 7. Actually have 7 rows. And then it has 18 columns. If you go from here, this is column 1, column 2. This will be column 3. We're going to have column 4, column 5, column 6, column 7, column 8, column 9, column 10, column 11, column 12. Then this will be 13, 14, 15, 16, 17, and 18. That is why we have 8 columns, which corresponds to the 18 groups or families of elements in the periodic table. So this is the basic arrangement of the modern periodic table. Now, the periodic table has undergone a lot of changes and evolution in the recent past, whereby there are different conventions that are being used in the periodic table. Now, the US convention uses the Roman numeral and a letter, either A or B, at the top of the column to represent the families of elements. Whereas the IUPAC nomenclature, just like the one I wrote already, the IUPAC nomenclature not universally used numbers from 1 to 18, which is just exactly what I have done. So there are generally 18 groups, but the American system prefers to use a little bit of an older version. But I usually tell students using that older version makes more sense and easy for students to comprehend. Another striking thing about the periodic table is that if you look at the first one I showed you, I didn't show you any elements below. Now, the modern periodic table has number 58 to 71 of these elements, and number 90 to 103 are placed in, and they are not placed in their correct order. They are rather placed under the periodic table. And these particular groups are actually what we call the inner transition metals. And we're going to see. So if we compare this video, I want to show you the first one. If you look at this one now, from here to here are these inner transition metals that have been cut out and placed under the new periodic table. You see this portion is where we place them. This is where we place those inner transition metals. We call them the inner transition metals. Inner transition metals. So if you look at the real periodic table, you have these guys at this portion. See where you have those guys from 58 to 71 and from 90 to 103 are actually placed at this form of the periodic table because of their peculiar properties, as we're going to see. So if you look at, again, if you compare this, look at the two, and this periodic table has the two basic designation system. Now, the first one is the IUPAC nomenclature, the IUPAC system, which counts 1 to 18 now. Now, but look at the American system, uses group 1A. I say uses the Roman numeral and an alphabet. This is group 2A. This is group 3B. This is group 4B. We're going to see later why this American system is important. I don't want to let the cat out of the bag so early, but we're going to get to that. Again, group 13 here is group 3A, group 4A, group 5A, 6A, 7A, 8A, which constitute the last group. So these guys are the group 8A or the group 18. Of course, what we call these guys are the noble gases. We're going to understand why they have this kind of beautiful name actually in the first place. All right, so moving forward, I think that I'm going to write down my noble gases very much well. I don't think I like what I wrote there early. All right, okay, let me make it much better. So this is noble. Okay, I think I'm going to make that thing better. I have the potential of making it look better. So this is noble gases. All right, that looks better now. Okay, so moving on to the next thing, group and period identification. You see, every element in the periodic table has a particular group and has a particular period in which it can be found. Remember, every table, every table has a period, has a column and a row. Like I said earlier, the group is the column, the period is the row. So this thing has it. So we can locate elements based on that. Examples here, if you look at the first examples I have here, you see them. So potassium, of course, is a group 1 element. It's element number 19. Is a group 1A element according to the American designation, which is group 1 in periodic table, and is in period 4. So if you're looking at your periodic table, you're going to see that. Just try to look at your periodic table and see that. So let me go back a little bit. So this is, of course, if you look at this picture now, this is potassium number 19. It is if you trace it, it is in group 1 from here. It's in group 1 and it is in period 4. So every element can actually be identified that way. And I want to ask you that as you watch this video, you keep your periodic table by your side so that at any point in time, you can use that to make a reference and understand the lecture particularly. Zinc is an element number 30. It is located in group 2b. Look at it. It's located in group 2b and in period 4. Again, fluorine is element number 9. It's located in group 7a and it is in period 2. Barium, again, on the other hand, is element number 56. It's located in group 2a and is in period 6. So I want you to try out some of these things in your periodic table. If you look at this problem 1, I will advise you to pause this video, take a look at this question, use your periodic table to make these identifications and come back to it once again as we continue. So now I solved the problem. Selenium. If you look at your periodic table very well, I'm looking at mine as I'm talking to you. Selenium is in group 8. I want you to use the American designation. No need to use the IUPAC now. So this is in group 8. Group 8. And in group 8, we use, sorry, not group 8. That's a costly mistake. I'm very, very sorry. So I can't be saying group 8. Selenium is in group 6. So I should be looking at the periodic table. I'm looking at it, but I read it wrongly. So this is group 6A, not group 8, please. It is, if I look at the period now, I'm looking at the period selenium, it is in period 4. It is in period 4. So again, let's look at vanadium. Vanadium, I'm looking at it. Vanadium is in group 5B. If I look at it, so it is in group 5B. Again, it is in period what? It is in period 4. That is what it is in period 4. I look at element number 48. Element number 48, let's see. Element number 48 is cadmium, CD. Element number 48 actually is cadmium. And cadmium, as I see it, cadmium is in group, CD is in group 2B. It's group 2B. And it is in period 5. Cadmium is in period 5. Period 5. Again, element number 35. What element is element number 30? Element number 35 is bromine. Bromine again is in what group? Bromine, of course, is a halogen, is in group 7A. Group 7A. You put your group 7A. Again, bromine is in period 4. So you can use these designations to identify the location of every element in the periodic table according to the rows and the columns. The Bohr's model of the atom. You see, Niels Bohr was one of the early proponents of the structure of the atom and the arrangement of electrons around the atom. Bohr's model, although not completely not used now, but it opened door to a better understanding on both the structure and the arrangement of electrons around the atom. Of course, in earlier chapters, we've talked about the structure of atom having a centrally placed nucleus and a cloud of electrons moving around this nucleus. So Bohr proposed that he actually worked on the hydrogen atom. He proposed that in a hydrogen atom, that electrons moved. Oh, I missed that. You see that electrons in a hydrogen atom moves in concentric circles or orbits around the nucleus. If you look at the circle I draw here, I tried to get this and draw it from one of my software. This is the centrally placed nucleus. These are a series of concentric circles. And these circles, he called them, I have it there, the orbit. I have it there written. He called them the orbit. And inside this orbit, electrons will move around the nucleus. And he said this orbit corresponds to different energy levels, actually. Different energy levels. These different energy levels can be 1, 2, 3, 4 to infinity. He called these different energy levels. Now, by infinity, I'm not a mathematician, but I remember. Yeah, okay. So, he also said that electrons can change orbit. Now, an electron that is on a higher energy state can drop down, releasing or losing energy, and the ones that is in a lower energy state can actually jump up to a higher energy state, in that process absorbing energy. And he actually thought that this is the way electrons are arranged in the periodic table. He made a lot of success with this at that time, but in the 19th century, this theory was actually debunked completely when the quantum mechanical model came. Now, the quantum mechanical model is not part of what we're going to be doing in this class that much, but there are a few things we need to know about that. Now, in this model states that it is impossible to locate both the position and the speed of an electron in an atom. In fact, this scientist worked hard, labored hard to calculate both the position and speed of an electron in an atom, and it became practically impossible. Now, they came up with a conclusion, what we call the uncertainty principle, that is uncertain to do that. So you either locate the position or leave the speed, or you either get the speed or leave the position. However, they said that there is the location of an electron around the nucleus is only a matter of probability. So, and that probability is actually called orbital. So, orbital itself is defined as that region in space of a nucleus where there is the probability of finding an electron. What that simply means is that if you have a probability of finding an electron, you can also go there without having to find any electron, because every probability has another level of improbability or uncertainty. However, they hypothesized that there are different shapes of these orbitals, that these areas you can see these orbitals with a higher probability have different shapes. And of course, that gives birth to different types of orbitals. So there are basically 5 types of orbital currently we're going to be looking at: the s orbital, the p orbital, the d orbital, the f orbital. They have different shapes, and these shapes corresponds to different pattern, cloud-like patterns, where there is the highest probability of seeing an electron. Now, what I want you to do is just to understand the shapes of these orbitals and be able to at least draw them if you see them in exam. Now, the s orbital has a spherical structure. As you can see, the green, the axis, the 3-dimensional axis is there, and then it is spherical in nature. Now, the p orbital has a dumbbell shape. In fact, there are 3 p orbitals, because each of them lie in this plane into the pz, the py, and the px. And then there is what? The d orbital. The d orbital has a clover leaf structure. There is actually more d orbitals, but at this level, this is what we're going to be focusing with respect to this class. So the shapes of these orbitals are very, very important for you to know them. Again, I said the spherical one is the s orbital, the p orbital is a dumbbell, and the d orbital is a clover leaf. Now, valence shell electrons. So we'll now begin to understand what actually determines the chemical reactivity of an atom. Now, the valence shell corresponds to the outermost shell of an element that contains electrons. Those electrons contained in this shell are called the valence electron. They're called valence electrons, electrons that are contained in the outermost shell. Now, atoms with the same electrons in their valence shell will have similar elemental chemical properties. And in fact, not just that, they are located, very most important, they are located at the same groups in the periodic table. So the basic determination for the location of elements in the periodic table is based on the number of electrons they have in their outermost shell, or what we call, according to the valence electron. Why? Because the valence electron actually determines the valence electron determines the chemical reactivity. The chemical reactivity of an element. This is very, very important. The valence electron is what determines the chemical reactivity. So the whole chemistry we are studying is all about these valence electrons. So if you look at a few of these guys now, the lithium, sodium, and potassium are in group 1, including hydrogen, because all of them have 1 electron in the outermost shell. Again, group 2, beryllium, magnesium, and calcium all have what? 2 electrons in their outermost shell. That's why they're located in group 2. So again, this will be our group 2A. This will be group 1. This is group 1. I don't have enough space to put that there, 1A. This will be group 3. These guys here, 3A. This will be group 4A. This will be group 5A. This will be group 6A. This will be group 7A. And this will be group 8A. Of course, the group 8A are the noble gases. And the reason why these guys are grouped is that these ones have 2 electrons in the outermost shell. These guys have 2. These guys have what? No, these guys have 2, 3, 4, 5, 6, 7, and 8 respectively. And that is why they are placed in these particular groupings. And we're going to see the import of this. So this table shows you electron occupancy of shells. You see, hydrogen is in group 1, of course. What it means, it has 1 electron in the outermost shell. So the first energy level is the energy level 1, or we call it the innermost shell, the first shell. The first shell 1, or the orbit, according to the Bohr's model, will contain only 1 electron. Helium contains 2 electrons, will still be in that shell. Helium is the only gas that is odd. It is in group 8, but it only has 2 electrons. And we're going to understand this implication as we move on in this class. Lithium, again, is in group 1. Of course, is in group 1. It has to have only 1 electron in that. So the first shell is full. It goes to, look at it now. So look at lithium. Lithium is number 3. The first shell is now full because the first shell only accepts 2 electrons. It goes to the second shell and it has 1 electron in the outermost shell. If you go down, beryllium has 2 electrons in the outermost shell. Boron 3 electrons. So each of these elements are placed here based on the number of electrons they have in the outermost shell. So to make it easy again, let's extrapolate. Let's see, helium has 1 electron in the outermost shell. Let's compare that with another thing in the group. If you look at your periodic table, after lithium, you have sodium. Okay, let's trace it. Sodium is number 11. Sodium has 1 electron in the outermost shell again. Again, another one after sodium, what do we have? Potassium. Let's look at potassium again. Potassium has 1 electron in the outermost shell. And that is why these 3 guys are all placed in group 1A of the periodic table, because they have 1 electron in the outermost shell. And this has very important implications. Now, the question is coming here now. You can always pause this video, try out the problems yourself, and always come back and then for proper comprehension. It says, using the periodic table, determine the number of electrons in the valence shell of element in, I just put all the groups there. Of course, group 1A, I'm just going to be writing it. So group 1A, we contain 1 electron. Group 2A, we contain 2 electrons. It's important for us to know this. This will have 1, I can just say 1 electron. I don't have to put 2. Group, okay, let me say 1 electron, 2 electrons. Group 3A, we have 3 electrons in the outermost shell. Now group 4A, we have what? Group 4A, we have 4 electrons. Then group 5A, let me go this way. Group 5A, we have 5 electrons. Then group 6A, we have 6 electrons. And then group 7A, we have 7 electrons. And group 8A, we have 8 electrons in the outermost shell. So, and we're going to understand the importance of this particular electrons in the outermost shell and use that to understand the chemistry of each of these atoms. Now, a question is coming. It says, how many electrons does phosphorus have in its valence shell? Now, when you look at your periodic table, phosphorus is in group what? Is in group 5. If you look at it, phosphorus is in group 5 of the periodic table. It's in group 5 of the periodic table. So, and what it means, because it's in group 5 of the periodic table, it must have 5 electrons in its outermost shell. And that is a simple way we can use in determining the number of electrons. We're just looking at their groups and figuring that out. So let's now move on to another important thing we need to understand. Like I said, this chapter is all about understanding the periodic table. Let's look at the element classification. Elements are classified using many criteria. At this place, we're going to be looking at 4 of these criteria. The first one, We can classify element based on its valence electron. Or you can say the highest, because the valence electron is the highest energy electron. Or we can say a distinguishing electron that distinguishes it chemically. That's what we mean. Or we can say the blocks. A few books uses blocks, and we're going to talk about that as we move on. Now, it can be classified either as a noble gas or an inert gas. It can be, some elements can be classified as representative element, or we call them the main group, transition, or the inner transition. And then a more broader term, we classify them as metal, non-metal, or metalloid. So we're going to see different periodic table in the first one. Now, using the highest energy electron, or what we call the different blocks. You see, the periodic table is divided into different blocks. I want you to be looking at the periodic table. You see, those of them in group 1 and 2, the electrons are found in their highest energy electron is found in the s orbital. That is what it means, that s block. So both of the group 1 and group 2 elements are found in this group. The group 1 and group 2 are in the s block. Now, let's go to the right. Let's go to the p. The p groups are those elements that are from group, you look at this, this is group 3 in the American convention, is from group 3 to group 8. From group 3 to group 8 element, this is group 3. This is 3A. Do not forget, this is 3A. And at this point, this is group 8A. Now, from group 3A to group 8A, or from 13 to 18, are the P block. All elements in this column constitute the P block. Now, if you look at this group, remember what I told you about the periodic table, that some elements have been placed. Now, these elements are in between group 2, this is group 2A, elements between group 2A and group 3A are what we call the D block. The D block elements, we'll give them another name, I will talk about that, the transition. And then this element that have been cut out and pushed down the periodic table is what we call the F block. So it's important to understand the designation of this element, of this highest energy electron, as S, P, D, and F. I remember I didn't give you the F because of the complexity of the structure of the orbital. But what it simply means is that the electrons at the highest energy level is found in these orbitals. And that is what we mean by different blocks. Then we have another convention. We can classify them as either representative or main group elements. Representative or main group elements are elements in which the highest energy electrons are either, you remember earlier we talked about the S and P. All the S and P block are all representative elements except the group 8. We don't call this guy representative element because we call them one name noble gases, they are special. So if you look at that, the representative elements are the ones that we show in the, is this ash or gray color? So group 1A, group 2A, group 3A, 4A, 5A, 6A, and 7A are elements in the main group, call them the main group. And the reason why we call them the main group is that they are similar, their properties can be similar. We can make a determination that this element in this group will have a similar chemical properties. And that will not change. They have the same electron in the atomic shell. They can make that determination. We cannot make that determination with the rest of this group, particularly the yellow group. Let's look at those of them in the yellow group. The elements in the yellow group are the transition element. The transition elements have their highest electron found in the D orbital. Remember earlier we called them what? The D block. In this case, those D block can also be called the transition metal. And these elements are between group 2A and group 3A. We call them the transition. Now, those elements that have been, I call them the castaway elements because they have been cut out from the main periodic table and pushed down. They are called the inner transition element. And these elements are those ones that we find in the F subshell, or I call it the F block. So these guys are given a wonderful name. So they are called the inner transition element. And also they have a special name to them. We're going to talk about the special names. Okay, let's talk about the special names here. It doesn't matter. Now the special name here are the lanthanide and the actinide. The one at the first row here are the lanthanide. These guys are called the actinide. So we call them the lanthanide and actinide series. We have another classification here So just to tell you, this image was gotten from Wikipedia, and I got them from this place, and I said it is important I recognize that fact. So now, the biggest classification is the broadest, which will classify elements as metals and non-metals. You see, metals constitute 2/3 of the periodic table. When you look at the periodic table here, okay, let me move down first. You see, 2/3 of the periodic table to the left is made up of the metals. The metals are shown in blue. And then, if you go to the right, now, the right of the elements is 1/3. That 1/3, we call them the non-metals. So, what are the properties of metals? Remember, the metals are good heat and thermal. They're good thermal and electrical conductivity. They conduct heat and electricity very well. They are highly ductile, and they are malleable, and they have metallic luster. Remember, some of these things, what they mean. Of course, the one that might be confusing is ductility. Ductility simply means it can be drawn into a wire. Drawn into a wire. That is what ductility means. Ductility means can be drawn into wire. Again, malleability means when you beat it up, it can change shape. Malleability means change of shape. You can check those out with Common Dictionary. It changes shape when beaten. If you beat it, it changes shape when you beat it up, so it doesn't break. And then metallic luster simply means they are highly shiny, like your jewelry. They are very shiny, very, very shiny, and attract the eye. That's what I mean by metallic luster. Okay, well, let me make that shiny, very clear enough. I don't think that is clear as I want. Make it very clear enough. They are very shiny. Okay. Then, what about the non-metals? The non-metals have properties opposite of those of the metals. Complete opposite. What we know about them is that they usually occur as either solid, liquid, or gas. Most times they are powdery and brittle. Brittle means they can easily break. When you hit them, brittle means break easily. When you hit them, they will break into powder. They will break and become powder. So most of these are brittle. They are highly brittle. When you hit them, they just break. They are brittle. That's what we know. Whereas the metals are malleable. So when you look at the periodic table, it shows this. Again, I got this from Wikipedia. If you look at those of them to the 1/3 of the left here, this is our non-metals at this point. These are our non-metals. The metals are to the right. Then, if you look at the boundary between the metals and the non-metals, you see a special group of elements that we call the metalloid. They're called the metalloid because they share both the properties of the metals and the non-metals. So they are in between. They are in between. Depending on the condition, they can either behave as a metal or the non-metal. And in fact, I usually tell students that the discovery of these metalloids have actually revolutionized technology in the world. Today, Silicon Valley is built on silicon. And we'll talk about all the technology we have in life, the computers, the smart tablets. As I'm using it, even a smart tablet, a writing tablet now, it has grown the technology so well that at this point, we are talking about smarter technology every day. So again, the good examples we have here is the silicon, the commonest, germanium, boron, arsenic, and other ones in that group. So those guys are the guys that are separating the boundary between the metals and the non-metals, and we call them the metalloids, or you can say they are the semi-metals. You can also call them the semi-metals as well. You can call them the semi-metals. Now, let's move on to the next page, perhaps, which will constitute close to getting to an end of this lecture. It says, use the periodic table to determine the following for the following elements. SR is strontium. This is chlorine, selenium, xenon, molybdenum, and americium. It says, number 1, the valence shell electron position or the block. We want to determine the block. So the first question there, we want to determine the block in which all these elements behave. So this classification is based on the highest energy electron. So let's start with the first one, strontium. Strontium, it has 2 electrons. It's in group 2, and a group 2 element is located in the S block. Again, chlorine is in group 7. Group 7 element is located in the P block. Again, the next one is selenium. Selenium again is in group what? Selenium is in group 6. Group 6 elements are located where? They are located in the group 6 elements are located in the P block. I want you to look at your periodic table as you solve these problems. You can always pause this, solve the problems, and come back and check for your answers. So after selenium, what do we have there? We have xenon. Xenon again is also located in the P block. Xenon is located in the P block as well. And then what else? We have molybdenum. Molybdenum, Mo. If you look at Mo, Mo is located between group 2 and group 3. They are the guys we call the transition element, and it is the D block. The last but not the least, americium. If you look at americium, americium is number 95. Those ones that are the outcast, americium is located in the what? In the F block. So that is how we solve that problem. And then we do the last one, the second part, which is B. It says classification based on the representative transition, inner transition, and noble gas. So let's see. Now the first one we're going to see there is that, let me try to put those ones that are representative. Strontium is in P, is a representative of main group. So strontium, chlorine, selenium are all representative, or we call them the main group, representative or main group. They're in the main group. We call them the main group elements. They are the representative or the main group elements. And then the other one is what? So we have strontium, chlorine, selenium are all representative of the main group element. Then xenon, we classify xenon. Xenon is a noble gas. Noble gas. And then what else? Molybdenum. Molybdenum, if you look at molybdenum, is in the D block, and those D block guys are called what? The transition element. Transition elements. And then last but not the least, Am, americium, is located in the castaway box, and I call them, you can write that americium much better. I don't have a lot of space, but I'm going to fit it in there. So americium there, Am, is located in the F block, and those F block elements are called the inner transition element. Inner transition element. That's what we call them, the inner transition element. So this is how you solve this kind of problem. This kind of problem will usually give out this kind of problems in multiple choice. So just gonna watch out for those kind of questions. It could be tricky at times. Europium is an example of dash element. If you look at element europium, if you look at it very well, europium is an inner transition element, EU. Look at it there, EU. If you look at EU there, EU is number 63. It is in the inner transition element. You're going to, the correct answer is number 4. The next question. So which of the following is a transition metal? Which of the following is a transition metal? So if you look at them, potassium is not a transition metal. Plutonium, is it a transition metal? Look at it. No, it is not a transition metal. Rubidium, is it a transition metal? No, it's located in S block. It is not. And the only guy that qualifies, as a transition metal is what? Gold. Gold becomes the correct answer, because when you look at gold, gold is number 79, is in the D block. The D block elements are those guys that are called the transition elements. We now go to the next one. It says, which of the following is a metalloid? Of course, potassium is not a metalloid. We know that, clear enough. Selenium is not a metalloid. Gallium is not a metalloid. The only metalloid we have here is number 2, and that is germanium. And germanium is element number 32, of course. Is the element number 32. And if you look at it there, it is shaded green. It is a semi-metal or a metalloid. You call it metalloid or semi-metal. Semi-metal. Semi-metal or metalloid. All right. And the next, that could be potentially the last one. It says, okay, I think that is actually the end of the problem. I thought we still have another one. That was the last one in this lecture. Thank you once again for listening to this lecture. Once again, we're going to see in class. If you have any questions, do not forget once again that the best channel to reach me is to send me Canvas emails or send me Canvas messages or send me emails in my email eudenze@yvcc.edu, or you can always come and see me in the office. Thank you for listening once again. I will see you in class. Bye.